So today we will talk about Spark, right? Yet another big data system, very popular, um, which came out of Berkeley in 10 years ago, right? But before that, let us quickly revisit what we were looking at yesterday. So we started with we want to do distributed computation, and the most straightforward approach is to do distributed shared memory, right? So the threads that were already running on your laptop or a single machine, you just spread them across on a distributed setup. So we saw a realization of DSM with page-based DSM, right, where we are building DSM inside the OS. So we saw a few problems with it. So one problem we saw was fault sharing, right? Here one thread is incrementing x in a loop, another thread is incrementing y in a loop, and these two x and y happen to be on the same page, right? So they are independent variables, but they happen to be on the same page. So we will keep on ping-ponging the page, right? So, right. Then we looked at another major issue, which is fault tolerance. And for fault tolerance, we talked about two approaches. So first approach was creating checkpoints, right? But we were worried about the consistency of the checkpoint, right? So checkpoints, either we stop the world, right? We stop all the execution, create a checkpoint, and then resume execution. Or if we don't want to stop the world, then maybe we want to create checkpoints as the code is executing. But that can have issues. So for instance, let us say there is a simple program which is incrementing x, and y is y plus x in a loop, right? So initially let us say x is 1 and y is 1, and let us just say they are on separate pages, right? So now we don't want to stop the program while creating checkpoints. So let us say x creates a checkpoint immediately, then we increment x to 2, right? So the code is running, and y becomes 2, right? And then we create a checkpoint for y. Sorry, y becomes 3, right? So 2 plus 1, right? So if we are creating checkpoints while the code is running, we may end up in such situations, right? So we first created a checkpoint of page containing x, and in the meantime the code modified x, the code also modified y, and then at a later stage we checkpointed y, right? And the code continues to run. So now x is 3 and y is 6, right? But now let us say the system crashes, right? And we want to recover from the checkpoint, right? So when we recover from the checkpoint, we get x as 1 and y is 3, right? And if we continue executing this code, after recovering from checkpoint, we will see that x becomes 2 and y becomes 5, right? So we ended up in a inconsistent state, which would not have been possible if the code didn't crash, right? So we are worried about the consistency of checkpoints, right? So one approach is we stop the world, create a checkpoint, resume, right? But that is too slow. So it would be great if we can create checkpoint while the code is running, but then we may end up with inconsistent checkpoints, right? Which take us to states that were never possible.
Can't we have timestamps for assigning?
Right. So we will look at how to get around this today, right? We will look at how to create consistent checkpoints even though code is still running. The other problem is once you crash, you want to start from the checkpoint and continue forward, right? But it will be great if you only have to roll back what you lost, right? So for instance, if for instance you only have to re-execute this part of the code, right? And you don't have to re-execute y equals to 3, right? You don't recompute what you did not lose, right? So let us say this page was already still there in a different machine, right? But the page containing x is lost. So it will be great if we didn't have to recompute y, because we actually didn't lose it. Then the other issue with DSM that we saw, so in fault tolerance, the other approach that we discussed was replication, right? That instead of keeping a page locally, we will keep the page across machines, right? So even if we lose a machine, hopefully the page is not lost. But we discussed this can be terribly slow because local writes become remote writes. And we were also worried about consistency, right? So one machine thinks x is equal to 2, another thinks x is 3, right? So now we end up with diverging pages. Then, so because of these hard problems, we gave up on general purpose computation, right? And MapReduce came along and said, if your computation can be expressed as a map function and a reduce function, then they will take care of all of this, right? They will take care of locality, they will take care of fault tolerance and stragglers, right? And the reason they choose MapReduce is, first of all, MapReduce is embarrassingly parallel, right? So there is lot of opportunity for parallelization. And secondly, lot of problems that Google was interested in could be expressed as MapReduce, right? So both of those stars aligned, and they implemented MapReduce. So anyone remembers what was our approach for locality? How do we get locality in MapReduce?
While assigning the thread, while assigning the file to one, master takes care that if the file is already existing in one of the workers, it will assign that same.
Right. So master tries to put a task on worker that is close to the data, right? So hopefully it is the one that has the data. If it does not have the data, then hopefully it is in the same rack, right? So it doesn't have to cross the entire data center and stuff like that.
So don't you think it will be more centralized kind of a thing? Like, yes, there might be a possibility of master not working, but still, it is a dependent thing.
Yeah, so in the paper's implementation, we are not tolerant to master failures. So if master crashes, the job fails. Okay, anyone remembers how we did fault tolerance?
If something fails, to restart the thread afresh.
Right, so if after map task runs, worker crashes, we just restart the map task. And the suggestion is that it's good to keep map task deterministic, because otherwise some reducers will see output of first execution of map task, and another reducer might see the output from the second execution of map task. Right, so it's good to have deterministic tasks for fault tolerance, because we are going to re-execute stuff. And because tasks can run multiple times, if they are making side effects, we would also like idempotence, right? Okay, any questions on this? Okay, cool. So today we'll talk about Spark. So Spark borrows heavily from MapReduce, right? All of these ideas that tasks should be deterministic, and for fault tolerance just re-execute the task, and for locality try to place the task on a worker which is close to the data. right? All of this, and then there is a central master and some workers around it. So all this is same in Spark, right? But there are some curious differences. And the paper also does some interesting commentary on DSM, right, distributed shared memory, and tries to fix the issues that are there in DSM, right? So let's revisit this problem of inconsistent checkpoints. Right, so we were running this code in a for loop, right? And the issue that we saw was different pages may be checkpointed at different times. Right, and when you crash, you might end up creating a state that was not possible. So the suggestion or the observation of Spark is this problem happens because you allow mutating a variable after it was checkpointed, right? So x was already checkpointed to storage, but after that you allowed changing x to 2, right? But if I can say that variables are immutable, right? So I now number them as x0, which is different from x1, right? So if variables are immutable, then we don't get confused between x0 and x1, right? So let us say we create this checkpoint, right? And then we crash, right? So when we crash, we have lost all of this, right? Because these were not in checkpoints, and we have also lost this. So then when we resume from the checkpoint, we have to calculate x1, right? And x1 can be calculated from x0, right? So how it is exactly done, we will get to that in a little bit. And then when we want to calculate x2, we can calculate that from x1. And then when we calculate y2, we can calculate that from y1 and x2. Right? So we end up in a state which is consistent. Right? So the state before the crash and the state after the crash is the same. So the problem really happened because of this mutability. Right? So once things were written, we allowed modifying them, right? And then when we recovered, we got inconsistent x and y's. So the first big idea of Spark is make all objects immutable, right? Once you have written them, you cannot change them, right? So that whenever you recover from checkpoint, you are sure that you got the right variable. So this immutability is quite a big idea. It sounds pretty not a big deal, but it also helps you in the application, right? So remember we were worried about x equals 2 and x equals 3 diverging from each other, right? But if I can say that variables are immutable, so once they are written, x0 can never become anything else, right? So even if I create 1,000 copies, there is no way the copies will diverge, right? Because x0 is immutable. It cannot be changed once it is written, right? So we also got around from the problem of consistency during replication, right? We are sure because variables cannot be changed, I can just create as many copies as I want without worrying about their consistency. So the second idea is of what is called lineage, right? So yeah.
How do we know which xi is the latest xi when we use
Yeah, so we will get to actual Spark and then things should become more clear. But the idea is immutability, right? So once x0 is written, you cannot change it. But we will look at actual code of Spark and re-look at all these, right? Any other questions? Okay, so the second idea is lineage, that you only need to recompute. So let us say I was interested in y2 equals to, I was interested in this variable y2, right? So if I know that y2 depends on y1 and x2, and if y1 is already in checkpoint, I don't need to re-execute this, right? So I can just recover from y1, and because x2 is lost, x2 depends on x1, and x1 is lost, x1 depends on x0. So x0 is in checkpoint. So I just re-execute what I lost, right? I don't want to re-execute what I did not lose, right? So this lineage remembers which variable depends on what variable, right? And yeah.
x0 may also depend on y0, so like you might need to build a value y also.
like also you are putting a dependency like there is a
Yeah, so dependency is a DAG, right? There are no cycles in the dependency, first of all.
So like for y, you will, apart from remembering the latest value y2, you will also need to remember the older values y1 and y2.
Why?
Because x0 might depend on y0.
So x0 is already in checkpoint, right?
x1 might depend on y0 and x0 both.
Right. So if I'm interested in y2, I can follow this lineage graph backwards, right? And I don't have to follow it backwards as soon as I hit a checkpoint, right? But if I don't hit a checkpoint, I have to keep following it backwards. So basically what you're saying is, let us say x2 had a dependency on y0, right? So then we will have to recompute y0. Right? So we stop going backwards as soon as we hit a checkpoint, right? And from there we can execute forward, right? So that is roughly the idea of lineage. But we will look at it in more.
like as you were saying that main objective of Spark is that objects are immutable. So you are just reading the previous values and computing the future values.
Yeah.
So is it something like Paxos? Yeah.
No, no, no. Paxos is completely.
Like in Raft and Paxos also we have this immutability things. So
Yeah. So we will look at Raft in next lecture. Let's not get confused, right? So Raft and Paxos are about quorums, right? So this is, we are talking about computation right now, right? So there is no replication as of now, right? There is only a single copy of x and y's, right? At some points they are checkpointed, and if things crash, we lose the most recent x and y's, right? Yeah.
But you made a very interesting point there, sir. So you said that if there is a dependency from x1 to y0,
Mm-hmm.
then we, like the algorithm you mentioned about traversing the graph backwards until we hit a checkpoint, we'll have to anyway go ahead and recompute y0 then in that case.
Yep.
Then that defeats the purpose of a checkpoint.
No, so
at
hopefully,
y1, the reason we have a checkpoint at y1, it indicates that up to this point, all the computations before that has been stored, and therefore we don't need to recompute that. That's the meaning of a checkpoint. So if you have to go behind y1 and compute something else, that defeats the purpose of a checkpoint itself.
let's revisit this when we actually look at Spark, right? So right now we are just looking at the concepts in Spark, but once we start looking at actual Spark implementation, then we can revisit this question. Okay, so any issue with this re-execution? So by the way, this should sound familiar, right? This is exactly what MapReduce was doing, right? So just re-execute. When things crash, just rerun the map task, right? So it is a similar idea that when things have crashed, just re-execute from checkpoint. So any issue with re-execution?
Overhead increases again and again. If there is a fault occurring, so again that will be executed. There is no checkpointing, so overhead increases.
Yeah, so when to checkpoint is a optimization problem, right? So if you never checkpoint, then you have to basically re-execute the entire program again. But if you checkpoint too often, maybe there is overhead of checkpointing. So that is an optimization problem. So the other issue is the same issue that MapReduce had, that all these transformations should be deterministic, right? If these transformations are non-deterministic, we may again end up in inconsistent states, right? So I hope that is obvious. Okay, so this is the overall plan. So we have objects that are immutable. We'll manage lineage. When things crash, we will re-execute from the checkpoint by going forward in the lineage. But this should make us a little uncomfortable, right? So far I'm claiming that we'll maintain lineage across every variable modification, right? So the lineage graph itself is going to get humongous, right? So every time x is changed, I will manage this lineage, right? And I will have to manage every copy of x in this lineage graph, right? So the lineage graph itself is going to get humongous. So the idea there is, the main idea is control the size of the lineage graph, right? So don't allow such fine-grained updates, right? Don't allow such things that you are changing a single integer, right? So again, this is about the similar idea we saw yesterday. Restrict the programming model to help us build a system that can automatically handle fault tolerance. So the idea is don't allow such fine-grained transformations, only allow coarse-grained transformations, right? So we will see what that means in a minute. So I think it is time to start looking at actual Spark code. Okay, so this is a Spark program, right? This program reads a text file from a distributed file system, right? And then it is just trying to see whether it is trying to filter out the lines which starts with a certain keyword, right? So there is like a grep that we are trying to implement. So this looks very much like a regular program that you would write on your laptop, right? So that is the beauty, right? So we are trying to provide an interface where the programming model is just like you program on a single machine, right? But in reality, this is going to execute in a distributed setting. So the trick is these lines and these errors, these are not your regular variables, right? These are, in Spark terminology, these are called RDDs, which stands for resilient distributed datasets, right? So Spark calls them RDDs, but basically they are just collections, right? So lines is just a collection of lines, right? And errors is just a collection of errors, but they are also distributed, right? So this entire collection is held across different workers. So this is the same idea as DSM, right? So this is only a single object. From a programmer's point of view, it's a single object, but this object is spread across workers. So let us see how this program will actually run, right? So just this small program. So let us say we have 3 workers, worker 2, worker 1 and 3. So each of them, let us say, had a HDFS block, right? So this is a huge file, terabytes of file. So the file itself is split across workers. So each worker let us say holds a block of the file, right? So this whole thing is being referred to as lines. So this object is split across different workers, but this whole thing is a single RDD called lines, right? And this RDD has 3 partitions. It is spread across 3 workers. So now when we want to execute this line, this can be executed locally, right? So we filter out all the lines starting with error, right? So each worker can do this locally without having to talk to each other, right? So again, this whole thing, this thing is called errors, right? And this is yet another RDD, right? So RDD is a collection of strings in this case, which is partitioned across workers, right? But from the programmer's perspective, it's just a variable. Makes sense, right? So you wrote such a simple program, but it is actually executing in a distributed manner. Any questions? Okay, so so Spark has a similar architecture as MapReduce. There is a central manager which they call driver. There are bunch of workers, right? So driver in MapReduce, driver used to remember the tasks that it has to perform. So here the driver only has to perform remember RDDs, right? What are the different RDDs in the system, right? Where are their partitions, right? So what are the different partitions of this RDD? Which worker hold which partition, right? So remember, one partition can be held by multiple workers as well. So because RDDs are immutable, Spark may choose to create n copies of a partition and spread it across workers, right, without running into consistency problems. Yes.
When you're saying the partitions, these partitions the contents of the file
Yeah.
Across multiple.
Yes.
So what if the program or the problem you're trying to solve requires logic which is like line dependent? For example, if you want to say if this is line number 20 or if it's an odd numbered line, then do some logic. If it's an even numbered line, do some logic. Then partitioning this way also requires that the workers remember the parity of the line number.
Right. So remember I mentioned Spark only allows coarse grained transformations, right? So you can take an entire RDD, apply some transformation on it and convert it into a new RDD, right? So you are applying a coarse grained transformation called filter. But if you wanted to make fine grained transformations, like do something to line 1, something else to line 2, which could not be expressed like a map function, then you are pretty stuck with Spark, right? So Spark only allows coarse grained transformations. So any questions so far? Yeah. Okay. No, so RDD is a program variable basically, right? So lines is an RDD, but lines itself is partitioned across workers, right? So this whole thing is lines, right? But this lines is partitioned across workers, right? So every RDD has partitions. Okay. Then do you have another question? Right. So lines is the name of the RDD, and every RDD can have multiple partitions.
So by coarse grain, do you mean that lines as an input should be self-sufficient?
Self-sufficient.
I mean, it should not depend on other batches of lines.
No, that's
You
not the
cannot
case.
inspect an RDD. Is that what you mean to say?
Okay, so one example is, let us say one RDD was a ML model, right? So this is where Spark really fails, right? And why we needed TensorFlow, right? So let us say my RDD was ML model, right? So ML model is just a bunch of weights, right? So these weights are spread across different workers. So now when you are training, you have to update the weights, right? But you cannot write a map function for this update, right? You have to make fine-grained changes. So change weight number 3 to something, change weight number X, weight number 4 to something else, right? So that becomes a fine-grained update. Whereas here we are only trying to do coarse-grained updates. So that is change everything to something else, right? So multiply every number by 2, right? So Spark only focuses on doing coarse-grained transformations. Okay, so let's look at a fuller example. Any other questions on RDD? Yeah.
Not an RDD, but like when we say the variables are immutable in Spark and we maintain all variables separately, like x1, x0, x1, x2, all of that. So for x1 we maintain the state x0 and for x2 separately we maintain x0 and x1.
No, so we are maintaining RDDs, right? These are RDDs, right? And we are also maintaining the lineage. So lineage is how did I get, so errors was received from lines, and to receive errors from lines I had to apply this transformation, right? So RDDs, okay, so what,
Actually my question is in the previous slide, not
okay.
about RDD. So here we are maintaining lineage for each variable.
So lineage is for the overall execution. Lineage is for the overall execution, right? So yeah, but again this will become more clear when we see a more fuller example, right? This is a very simple example so far. Okay, so let's let's try to compute page rank using Spark, and this will also show all the benefits of Spark and also show why it is performs better than MapReduce, right? So let us say we are interested in computing page rank, right? And let us say we are given a very simple graph. Right? So this is a web graph where these are some web pages and web pages are pointing to other web pages. So this can be, I mean, page rank is not just about pages, right? This can be anything, right? Maybe these are actors and Shah Rukh Khan thinks Hrithik Roshan is a good actor, right? So we draw an edge. So the idea is if lot of people think that someone is a good actor, or if lot of people are linking to a page, then they are probably a important page or they are a good actor, right? So if you are U4 and if Shah Rukh Khan thinks you are a good actor, you are probably a very good actor, right? So a lot of people think that Shah Rukh Khan is a good actor. So that is the idea. So basically U1 and U3 should have a lower page rank than U2, right? Because no one thinks U1 and U3 are good actors. Except themselves. But two people at least think U2 is a good actor.
Which is not the edge which is independent will be given lower rank.
So yeah, so this is a, I mean this is an intuitive thing, right? If no one thinks that I am a good teacher, then I'm probably not a good teacher, right? But if lot of people think I'm a good teacher, then maybe I'm a good teacher. It's something, it's a very intuitive notion, right? So no one thinks U1 and U3 are good, so they should have a lower rank than U2. U1 and U3 should also have a lower rank than U4 because someone who was good thinks that U4 is pretty good, right? So they are pointing to U4. And U2 should have a lower rank than U4 right? Because U2 thinks U4 is a great actor, but U4 doesn't care about U2. So, so this is the idea of page rank, and we will implement it in Spark and see how it actually executes using RDDs, right? So, so the way the algorithm works is a iterative algorithm, right? So we basically simulate a random user, right? So we say a user will either go to a random page with certain probability, let us say 0.15 probability. So with 0.15 probability, they'll just go to any one of these pages. And with 0.85 probability, they will click on a random link that is on the page, right? So we are just simulating a random walk on the graph from a user, right? And if the user is, and the page rank is trying to capture how often the user ends up at the page, right? So if the user ends up at U4 lot more than they end up at U3, probabilistically speaking, then U4 has a higher page rank. So let us see how to run this algorithm. So let us say we start with links. Actually, let me go to the next page. So we start with links. So U1 is pointing out to U1, U2. U2 is pointing out to U2, U4. U3 is pointing to U3, U2. And U4 is only pointing out to U4. Right, these are our links. We can also initialize the ranks as a constant. So initially everyone has equal rank, right? So now what we need to do is we need to figure out that once someone is on that page, what is the probability to go on a different page, right? So once someone is on U1, the probability to go to U1 is 0.5 and the probability to go to U2 is also 0.5, right? So we are basically doing a join between these two, right? And then splitting this rank across the links, right? Then similarly from U2 I could go to U2 or I could go to U4 with equal probabilities. From U3 I could go to U3, I could go to U2. From U4 I could go to just U4. Right. So once I have calculated this contrib variable, then I can calculate the new rank. So for the new rank, I will have to sum up all the contribs of U1. So let us say I get 0.5. So this is multiplied by 0.85. This, and we add 0.15. So 0.15 is the probability that a random user will come to U1. So this becomes 0.575, right? This is the rank of new rank of U1. Then for U2 we find all the U2s, right? Sum them up, we get 1.5. Multiply 0.5, add 0.15, we end up with 1.425. For U3 we again only have a single U3. For U4, so two people are pointing to U4, so we get 1.5 into 0.85 plus 0.15. Right, so after single iteration, U1 and U3 are already ranking lower than U2 and U4. So this is an iterative algorithm which will, again we will use this ranks to again calculate contribs and then again calculate new set of ranks, right? So let us say I was interested in executing this using MapReduce, right? So we know how MapReduce works. So initially, also let us say that
When will it converge?
so it converges when ranks stop changing, right? At some point, ranks stop changing.
Okay, the same pattern is observed in 2 equations also.
Yeah. Or you can also run it for n iterations and just say I am done. So you can say,
It should be, change should be constant, right? Then only
yeah, so ideally you should run it to convergence. But if it is not converging, then you can say I will run it for million iterations or whatever. Million sounds too much, but and then I'll stop, right? Okay, so let us see how we can execute this using MapReduce, right? So we are given a file which is storing the adjacency list, right? Just a text file that u1 points to u2, u3 points to u2, and so on, right? So let us say this is a huge file, right? So it is already split into blocks, right? So one worker is holding the first block, the second worker is holding the second block. Is there a question? Can I?
So, like, what is why we are adding
0.15?
0.15? Like for the second, like for 0.85 is like the probability of taking a link, right?
Yeah.
And
So
0.15.
0.15 is user directly opened u1 in the browser, right? So they didn't.
user will open.
Huh?
Random user will open, so what will the probability of getting that link?
Yeah.
You mean they didn't reach U1 via following a link, they reached U1
Directly.
directly.
Yeah. Okay, so if we were to execute it using MapReduce, how would you do it? So maybe calculating the links itself is one MapReduce, right? So it needs, for U1 it needs data from all the mappers, right? Then U2 also needs data from all the mappers, right? So maybe we run a MapReduce task to just get the links, right? So once the MapReduce task finishes, we have our links, right? These links may now be stored in, these links will now be stored in our HDFS files, right? Or the cluster file system, right? So the output of MapReduce was being written to a cluster file system as our output files, right? So these links are now written to HDFS. So let us say we want to calculate contribs, right? So this is simply a map operation. So it can take u1 is right. So this is a map operation, right? And then again for calculating ranks, this is again a reduce operation, right? Because for u1 I need the u1's contrib from all the mappers, right? So this is yet another, we just did yet another MapReduce job, and we again load to a cluster file system, right? So basically doing iterative computation in MapReduce becomes slow because of this, right? So we are doing series of MapReduce, and every time one MapReduce job ends, we write to a cluster file system, and then we again start, then we again write to cluster file system, and then we again start, and so on. So the idea of Spark is, let's not do that, right? Let's keep everything in memory, right? Let's not hit the disk unnecessarily. So
There will be a chance, like, since it is in the memory, so it can be like storage point of view, and so it is also vulnerable, like, in terms of it can be lost also. So
yeah, so we'll look at fault tolerance. If a partition is lost, we will basically use lineage to recover it, but we'll look at it in a minute. Okay, so here is the code. So this is their laptop and they don't have Spark on it, so I will not be running this code, but you can install Spark and run it, right? So this is directly from Spark's repo on PageRank, right? So, but instead of running the whole code, we will step on it line by line and see what is going on, right? So this is what the code looks like. So we start with an input file. So this is a small input file that captures our web graph, right? So the first line is reading this input file basically, and getting this new variable, which is basically a RDD called lines, right? And if you collect the lines, you see this on the console, right? So basically it has read all the lines from the input file. Next, we would like to, yeah. Better? Okay, next we would like to change the lines into links, right? So instead of simple strings, they are changed to tuples, right? And to change to tuples, we applied a map function, right? This map function is just parsing the line, parsing a string and returning as a tuple, right? And when I look at it, it is just a collection of tuples. So again, this links. So by the way, we are working on a very small file, so everything is running locally. But you can imagine if this in is humongous, then all of these are RDDs and they are partitioned across workers, right? So then I can run another distinct command. So my file had a duplicate U2 U4, right? U2 U4 was appearing twice, so I can run another coarse grain transformation distinct to remove all the duplicates. Next, I am doing a group by. So once I do a group by, I am basically collecting all the targets for every source, right? So U1 for U1 is pointing to U2 U1, U3 is pointing to U2 U3, and so on. So this was the.
This is similar to reduce operation.
Yeah. So now we are at this point, right? We have found our links, right? So next, links can be mapped again to convert ranks. So we are assigning a rank of 1 to every URL in the link. Then we join the link and the ranks to compute the contribs, right? So I will not go over this line by line. You can look at it again later. But so the contribs now has this U2.5, U1.5, right? Same as what we had here, right? So we joined links with ranks to calculate contribs, right? So all of these are RDDs, right? Contribs is an RDD, ranks is an RDD. And then finally from contribs, I summed them up, right? And to get this R, and then I can calculate a new ranks by multiplying this by 0.85 and adding 0.15, right? And when I run this, I get the first iteration of the ranks, right? So let's also, so this is a walkthrough and you should look at it offline. But in the actual code, it's actually much smaller, right? So you don't have to create, you don't have to unroll the loop, right? So this is actually happening inside the for loop, right? So this is the iterative computation. So we keep getting new ranks after every round of the iteration. But we should remember that even though this is called ranks is still immutable, right? This is a slightly subtle point. So even though we are assigning to the same variable, but from the Spark's point of view, this is rank 0, rank 1, rank 2, right? So rank 0 is still immutable. We are not changing. Once RDD is written, it is immutable. Okay, any questions? Okay, we can look at, let's also look at the actual execution, how this will proceed. Right, so initially we start from the STFS file, right, and on different workers we have different blocks. Right, so this is my first RDD called lines, right. Then these lines were parsed into tuples, right. So this is going into a map function to I think it was called links 0, right. So links 0 is again an RDD, right, which is converting every string into tuples. Then we ran a distinct operation to remove duplicates, right. I think it was called links 1. So, but to do the distinct, you cannot do distinct locally, right. So if this had U2, U4 and this had U2, U4, you cannot just do distinct locally, right. So this was an operation similar to reduce, where everything starting from U2 went to a particular worker, everything starting from U1 went to another particular worker, just similar to map reduce, right. So now we ran distinct. Next we ran group by key, right. So but for group by key we already have everything belonging to U1 because we have already run distinct operation, right. So group by key is again a local operation for every worker, there is no communication. Next we calculated bootstrapped ranks by applying a map function, right. So again this is a local operation. Then we joined links with ranks, but because both links and ranks are partitioned using the same hash function, which is the URL, again this is a local operation, right. So using this join we calculated I forgot what it was, yeah, this variable called JJ, right. So basically this is how the program is executing, right. So every variable is an RDD which is split across workers, so it is very similar in flavor to distributed shared memory, right. So the object is split across workers and you can change one RDD to another RDD using a coarse grain transformation, right. Something like map, filter, join, group by key, reduce by key and so on, right. So these operations are pretty expensive, right, because we have to, every worker has to talk to each other, right. So these Spark calls them wide dependencies, but these operations are quite cheap, right, because worker doesn't need to coordinate with anyone else, we can just pipeline this execution, right. So Spark calls them narrow dependencies, it's just a term. Okay, but the good thing is all of this is in memory, right. So compared to MapReduce, we are not hitting the disk every time, we are not hitting HDFS, right, everything is in memory. Okay, so now we can talk about fault tolerance, because everything is in memory, things can crash, right. So let us say W3 crashes, right. So all of this is lost, right, because everything was in memory, right. So this for computing, so whenever the master or the driver realizes that we have lost partitions, right, it can just re-execute this on a new worker to recreate this partition, right. So remember, the HDFS is never lost, right. This we have not looked at storage, but the file is replicated, right. So we will recompute the whole partition by going forward from the lineage, right. But of course, if the lineage graph becomes big, then you don't want to go all the way back in history and recompute everything. So once in a while you can also checkpoint stuff, right. So maybe at every iteration you store ranks in the cluster file system, right. So now when W3 crashes and you are interested in recomputing JJ, you don't have to, you can just recover from the checkpoint, right. Then we don't have to recompute all this. So look at the lineage graph. Right, so this is the lineage graph for page rank. Every node here is a RDD. You can transform one RDD to another RDD using coarse-grained operators, not fine-grained operators, right. So the size of the RDDs remains small, and once in a while you can also checkpoint. So here maybe you checkpoint every time you compute ranks, right. Okay, so that is the idea of Spark. Any questions? By the way, to run PageRank, Spark is 20x faster than MapReduce because it is iterative and we are not hitting the disk in every iteration. Right.
So the links are static or dynamic?
Static.
If the links are static, we can just use matrix multiplication because we are.
Yeah, so that's okay. So you can also do that in Spark, but we just looked at one. So the idea is not to argue about PageRank algorithms. The idea is to understand Spark. Yeah. Any questions? Other questions? Okay, so just to compare with DSM and Spark. So DSM allowed arbitrary fine-grained updates, right? Whereas Spark only allows deterministic coarse-grained updates, right? So DSM ended up with when we were creating replication, if we replicate a page, we end up with consistency issues. Here, because RDDs are immutable, you can create as many copies of a partition as you like because RDDs are immutable. Here, creating checkpoint can be expensive because you have to checkpoint everything, whereas here you don't checkpoint everything, right? You just checkpoint where you want and re-execute from there, right? And the idea of fault tolerance is simply re-execution, right? So, but comparing with MapReduce, it is quite similar. So fault tolerance idea is the same. We just re-execute whatever we lose. The big difference is that it can support iterative computations. We don't have to go to the disk. Everything remains in memory. and it can also support new transformations like join, group by, map, right? So all those can be expressed as MapReduce, but from programming, ease of programming, it becomes easier.